Steinhauer here. Welcome back. I want to talk now about how we can measure distances to galaxies, and even more importantly, how we don't even know what galaxies are until we know how far away they are. And it brings us back to the early 1900s, 1920 in particular, where there was a great debate between two prominent, famous astronomers, Harlow Shapley and Heber Curtis. And the debate was over what these things are, the spiral nebulae as they were called then. And we really didn't know because we had no idea how far away they were. They could either be close objects that were fairly small or very distant objects that were very large. And we had no real way of distinguishing between them until we could figure out how far away they were. And so this debate in 1920, Harlow Shapley argued that these were small and in our galaxy, and maybe this is a cluster of stars or a forming cluster of stars, and that the Milky Way is the entire universe. He also argued that the sun was not at the center of the galaxy and was offset from the middle based on observations that he had made of globular clusters. Curtis, on the other hand, argued that these spiral nebulae are in fact what he called island universes. They are distinct and separate from the Milky Way and comparable in size to the Milky Way. He also, though, argued that the sun is at the center of our own galaxy. And so neither one of them won the debate that day because nobody really knew how far away these things were. And until you understand the distances to these objects, you really can't get a handle on any physical parameters of them. And in fact, Harlow Shapley ended up being wrong about the spiral nebulae, but right about where the sun is in the Milky Way. And Curtis was wrong about where the sun is in the galaxy, but right about what the spiral nebulae were. So it was kind of a draw, even in retrospect. They were right about different things. Anyway, how do we go about finding the distances to these objects? How can you do it? Well, there's two basic ways that you can go about measuring the distance to things. And that is standard candles or standard rods. The standard method of standard candles is the most important and the most prominently used. And that simply is that if you have an object whose luminosity you know, the further away that object is, the fainter it will appear to you. And so if you can find an object whose luminosity you know and measure its brightness, you can find the distance to that object. Here you see a literal candle and how faint it seems as it moves further and further away. Here you see an object, let's say in a galaxy that happens to be really bright, and the further away that galaxy is, even though all of these have the same luminosity, it looks fainter because as you go further away, the object gets fainter and fainter and fainter. Standard rods works in the same way. If you have an object like a ruler or a meter stick whose length you know, then the further that object gets away, the smaller that rod will appear, the smaller that ruler, that length will appear. And so if you know that a particular kind of galaxy always has the same diameter, you can use the physical size of that galaxy on the sky, the angular size on the sky, to determine how far away that galaxy is. Now, you have to, in all of these cases, calibrate this rod somehow. So you have to know some of these candles and their actual luminosity, which means that there have to be some of these whose distances you know from other reasons to calibrate the source, and then you can use it to determine the distance to objects that you don't know. Okay, let's see how this was done for the Andromeda Galaxy. It turns out that there's a region of the HR diagram called the instability strip. And stars that are in this region of the diagram are pulsationally unstable, which means that they physically get larger and smaller over a several day time scale. And that's interesting. These stars are important because they're among the most brightest stars in the HR diagram, which means you can pick them out in distant galaxies. And also, they have this cool property of being pulsational, of getting larger and smaller. And so here is an example of that. And you can see on the left how the brightness of the canonical star in this group, Delta Cephei, which is where it gets the name Cepheid variables, Delta Cephei, every 5.4 days, see pulses. It gets larger and it gets smaller. And over those pulses, it gets brighter as it's getting bigger. And then as it's getting smaller, it gets fainter. And then it starts the process over again and it gets larger and it gets fainter. This is what people typically think pulsars are. They're not. Those are spinning neutron stars. But Cepheid variables are actually this. They're pulsing, they're physically pulsing stars. So how does this help us? Well, it helps us because we know how far away Delta Cephei is, and we can figure out what its luminosity is. And there are lots of other Cepheid variables that are either close enough that we have parallax measurements for them, or they're in clusters, which we've been able to figure out the distance to in other ways. And when we plot a diagram of a Cepheid variable's absolute magnitude or its luminosity as a function of the orbit of the pulsational period, the period of this brightening and dimming, you get a very nice linear trend. And that's extremely useful. So what's going on here? Well, again, remember this is a strip, so there's lots of variation in the luminosity of these stars. There's also a large difference in the size of these stars. And the larger the star is, the more luminous it is. And the larger the star is also, the longer it takes to go through this pulsational cycle. And so the very, very most luminous and very largest of these Cepheid variables take a long time, up to 30 days, to go through one of these getting brighter and getting dimmer cycles. Whereas the less luminous ones, the smaller ones, go through this cycle much faster. And that provides an incredibly important result. And that is that if you can find one of these objects and measure how long it takes to go through one of these cycles, which is really easy. All you have to do is watch it and measure its brightness over several days and see how long it takes to go through one of these cycles. Once you do that, you can move on your relationship and figure out what the true luminosity of that object is. And then it becomes a standard candle. And if you know the absolute magnitude of that object and its luminosity, and you measure the apparent magnitude of that object, that will give you the distance to that object. And once you know the distance to one star in a galaxy, you know the distance to all of the stars in that galaxy. And that's how this was actually done. So you might remember the name Edwin Hubble. He featured in our last video. He was the first to do this for Andromeda. And in fact, this is the photographic plate that he used to discover these Cepheid variables in Andromeda. Here is the Andromeda galaxy itself. This is a plate that was taken on October 6, 1923. And lo and behold, he noticed by comparing this plate to previous plates that this star right here in the upper right-hand part of this plate was changing in brightness. And that gave him the opportunity to follow it, measure its brightness variation, see how long that took, and he was able to use that to determine the luminosity of that star, and by measuring the apparent brightness to determine the distance to the Andromeda galaxy. And lo and behold, it's way further away than anything that we know of in the Milky Way galaxy. Lo and behold, it's its own galaxy unto itself. And it turns out that Andromeda is even larger by about 50% than the Milky Way is. Okay, this is an important step and an important feature of understanding how distances are determined in astronomy in general. And it brings us to this very important diagram called the distance ladder, which is how we determine different distances to various things. And it's a logarithmic scale. So here is inside the solar system, here's a light year away, 1,000 light years away, 1,000,000 light years away, 1,000,000,000 light years away. Okay, so inside the solar system, we can use radar, right? We can bounce radio waves off of planets and time how long it takes those radio waves to come back and get very accurate distances within a few hours of objects in our solar system. For nearby stars, remember, we can use the stellar parallax. We can use the fact that nearby stars will appear to move against background stars as the Earth goes around the sun. And that takes us out even a little bit further than this because we've gotten some very good parallaxes from satellites that have launched recently. Another way that you can do it, but again, you have, so another way to do this is with main sequence fitting. We've done this in lab, and that is that if you have two clusters like the Hyades and the Pleiades, the more near one will have a main sequence that's significantly higher and brighter than the further away one. And you can use what the true brightness of these main sequence stars are to determine the distance to those clusters. This is a process called main sequence fitting. But you need to calibrate this, right? So we need to know how far away the Hyades is before we can use the Hyades as a tool to measure the distances to other clusters. So parallax is really the only geometric way to do it, and all of them are dependent on the parallax to calibrate them at some level. We've already talked about Cepheid variables. Here's the period luminosity relationship. But again, you need Cepheids in clusters that you've already determined the distance to calibrate the Cepheid variable relationship and how luminous those stars actually are. Now, these Cepheid variables are very bright, so they get us outside the galaxy, the Milky Way, and into nearby galaxies. But this is a ladder, right? Without parallax, we don't know how far away the main sequence stars are in clusters. Without cluster distances, we don't know the Cepheid variables, luminosity, and without Cepheids, we can't calibrate more distant standard candles that we need to measure distances to galaxies at the far edge of the universe. We'll talk about these two distance indicators coming up. But I wanted to show you that all of these, it is a ladder. And the more accurately you can do all of these lower ones, the more accurately you would get all these higher ones, because all these higher ones are dependent on all of the ones that came before it. And a small uncertainty in the parallax or the main sequence distance will propagate through to uncertainties in all of these other ones as well. So it's a ladder that's built up, but we have to have those small ones, this parallaxes, to even have a chance to get all of the other ones as well. Okay, we'll come back and in the next video talk about an important result that's coming out of understanding the distances to galaxies. See you then.